So yes, I'm going to present this oncoming project on laboratory modeling of gap leaping and intruding western boundary currents under different climate change scenarios. The project is led, as Joel said, by Stefano Pierini from the University of Naples, and done in collaboration with the Dutch group at Utrecht University with Professor Henk Dijkstra. So as Joel said, the project has to start next week, so it will last for 6 weeks, starting from the beginning of June until mid of July. So I will just give the motivation and an introduction on the subject. I will explain the experimental setup and the dynamic similarity and dimensionless parameters used to design the experiments. Okay, so first of it's not okay. Okay. So what are western boundary currents? Western boundary currents are very intense currents that flow along the western boundaries of the oceans and that are induced by a gradient of the Coriolis parameter between the equatorial regions and the poles. We have two main examples of such currents. The first one is the well-known Gulf Stream, which flows here along the east coast of the United States. And the second example of such a big current is the CoriolisII current flowing in front of China. So these western boundary currents are very important because because of the huge amount of heat that they transport from the equatorial regions toward the poles. It's well known the effect of the Gulf Stream making the climate milder in North Europe compared to other regions at the same latitudes. And because of the corresponding air-sea interaction, but also because they play an important role in sustaining the global ocean circulation. Okay, we focus here on the CoriolisII current in front of China. The base question here, and the novelty graph from this project, is to see what happens with these western boundary currents, with these jets, when they interact with gaps, which are represented here, for example, by the Luzon Strait. So there is part of the current which may detach from the main jet and intrude here into the South China Sea, or even here on the top of the Taiwan Island, as shown here by these two pictures here. We can have the current which deviates south and north of the Taiwan Island, and can intrude here in the South and East China Seas, producing local properties in terms of hydrology, local circulation, and affecting the local climate. There has been already previous experiments that has been conducted in the old Coriolis platform by Pierini, investigating these western boundary currents without gaps. And more recently, 10 years ago, from Chermet and Kuhl, there has been other experiments, but in a smaller scale installation on a rotating tank of 1 meter diameter, which were the first which investigated this effect of an interacting jet with gaps. And what they saw from these small-scale experiments is that we have a double effect. The first one is that we can have at the same time different steady states with penetrating where the current is penetrating the gap or leaping the gap. And also we can have some hysteresis effects, meaning that the penetrating or leaping character or tendency of this main jet depends on the history of the western boundary current. So the results coming from this study, so as they were performed in small-scale installations, the resolution and the extent of the western boundary current was limited to a few centimeters. So there is a need to make such experiments in a larger scale installation, so that we can have the development of the inertial boundary layer on a much wider scale, and also in terms of the meridional resolution of the resolution of the zonal velocity of the zonal profile of the meridional velocity. So this is the main motivation of this study. So here to the experimental setup, we see here a top view of the experimental tank, which is just 2 meters of diameter. On the side here, we have a channel in which we have here two pumps, which produces a uniform flow along this full channel. We have here an opening that produces at the beginning here, at this side of the platform, a quite uniform flow. And once here, we have here a topography, so the depth, the full depth of the water within the tank is decreasing from 80 centimeters to 30 centimeters. And this is the way how this gradient of the Coriolis parameter is modeled in laboratory experiments. So the equivalent of having a gradient of the Coriolis parameter on the Earth from the equator to the pole, we can simulate this by changing the depth of the topography, and we get the same effect. So we get here the formation of this boundary current. We have here fixed boundaries here and here. We have here a gap. So the variation parameters beside the rotation period will be the size of this gap and the presence of different vertical elements that represent islands. So we will change also the spacing between these various elements, and of course also the incoming velocity which give the different dynamical ranges and the climate change scenarios. And also we have additionally here these elements which represent a portion of an island, and we will vary here twice the angle. So the technique used is based on particle image velocimetry by seeding the flow with particles. We will use, of course, homogeneous fluid, and we will take the measurements on a horizontal plane parallel to the bottom of the tank, 15 centimeters below the surface. And the measurement, so this is a sketch of the experimental setup, which is built up now in these days, showing here this lateral channel here. The red region is the sloping region, this is the top region, the fixed boundaries and the gaps here with the island. And this is a top view of the measurement regions we will take with the PIB. So we will use 3 cameras which cover the total region with the gap on the western boundary current and below this and also these regions here to see what happens on the lateral side of the western boundary current. So to make this the experimental setup, the relevant non-dimensional parameters are obtained using the conservation of potential vorticity, the equation of potential for vorticity in quasi-geostrophic approximation, which is valid because we have quite low Rossby number. And so from this steady state, so from this non-dimensionalized equation, we get the three relevant parameters. The first one is this epsilon value multiplying the non-linear terms, and what is the and this epsilon parameter expresses it's given also by the ratio between the inertial size, the size of the inertial boundary layer to the horizontal dimension of the western boundary current, and that expresses the strength of the nonlinear terms, which play a very important role in real western boundary current. And we are able to produce a scale 1 for this parameter, and is in the experiments, this parameter is 2 or 3 order of magnitude larger than these other two non-dimensional parameters, which expresses the strength of the lateral and the bottom, the bottom friction. Okay, so of course, with respect, we will be able. The fact that we are in scale 1 for this parameter means that we are able to reproduce the inertial boundary layer, but for these other two non-dimensional parameters, we will not be able to reproduce in scale the viscous boundary layers as compared to the real case. So, and well, the conclusion will follow soon after performing the experiments. Thank you.
So maybe there are already questions when the experiment didn't start.
No, just one. How long is each experiment planned?
So the good point is that compared to previous experiments of this type, this experimental setup will allow to have a quite long duration of the experiment. So the idea is to have, I think, in the order of half an hour for each flow rate. But yes, yes, of measurements, yes, yeah. Yes, the time
Yes,
will be.
in the previous experiment that they did in Trondheim.
They did it in Trondheim, and they used yes, but they used a piston to produce the base current. Yes.
Yes,
So the piston moved, and once it moved, then we will use a continuous source here, so that we get a continuous circulation, so we can last the experiment as much time as we want.
Probably after a certain time, you have some people who would have several
yeah.
Maybe
So maybe they will be confined. I don't know. Yes.
Yes, the difference also in Trondheim, they didn't have the barrier. In Trondheim, they didn't look at this problem of island.
This
yes. This is the main novelty is this island problem.
I think it's a very unclear problem, because it's not so straightforward to say how much of the main jet is going through the barrier and how much is staying here, if it's rather leaping or intruding, penetrating into the gaps. And also I found interesting is that in fact the transition from leaping to penetrating is not the same for the main flow as going back to the system. So there is an hysteresis which is not well understood. And the interesting thing is that here with such a setup, we are able to have a long